Okay, the following problem is designed to look at and use conservation of energy and conservation of momentum when appropriate. This is going to piggyback off Thursday and Friday's lessons in class where we discuss what happens during a collision and when it's appropriate to use energy and when it's appropriate to use momentum. Okay, the really poor drawing you have in front of you is the following. A 1 kilogram cart rests atop a 20-meter high hill that is frictionless. At the bottom rests a 3 kilogram cart. Two carts collide. The 1 kilogram cart continues to move forward at 2 meters per second. Will the 3 kilogram cart be able to make it over the 1 meter high hill with a speed of 4 meters per second? So essentially, we're looking for the velocity after the collision of the 3 meter high cart to see if it gets up over that 1 meter high hill. So we really need to know the velocity of the 3 kilogram cart, okay, at the top of that 1 meter high hill. All right, so let's look at this first scenario. We're going to mark this A to B. B here is going to be right before the collision. C will be right after the collision. And D will be on top of the hill. All right, so if we go from A to B, if we look at this from A to B, A is going to, the 1 kilogram mass is going down a frictionless hill. So if we consider from A to B, our system being the 1 kilogram mass and the Earth, okay, it will have gravitational potential energy. That gravitational potential energy will be transformed in kinetic energy, and we can find the speed of the 1 kilogram cart right before the collision. So we can look at this in terms of UG of the 1 kilogram cart at the top of the hill will equal the kinetic energy of the 1 kilogram cart at the bottom of the hill. This will enable us to determine the speed of the 1 kilogram mass right before the collision. So we're going to have the mass of the 1 kilogram cart times your gravitational field constant is equal, or times the height of the hill is equal to 1/2 the mass of the 1 kilogram cart times the speed right at B. So masses will divide out. We can multiply through by 2, so we get 2GH is equal to V squared. Take the square root of both sides. So we get radical 2GH is equal to V at B. Okay, so the velocity of the 1 kilogram object at B will equal 2 times 10 times 20. So 2 times 10 times 20 is 400. Take the square root of 400, you get 20 meters per second is equal to the speed at B. All right, so we now know at B, before the collision, we know the speed of the 1 kilogram cart is 20 meters per second. All right, so there's the 1 kilogram cart, there's the 3 kilogram cart. It's moving really fast. The two are going to collide. Now in a collision, as we found out last week, momentum is conserved and energy is not conserved. So we have to use momentum here. So from B to C, all right, we have our system would be, in this case, since I'm going to use both objects and we don't know anything about the impulse, will be the 1 kilogram mass and the 3 kilogram mass. All right, so we have, before the collision, we have the 1 kilogram mass moving at 20 meters per second. And then after the collision, we have the 1 kilogram mass moving at 2 meters per second. Okay, this is outlined, it continues moving in. So we need to know essentially the momentum of the 3 kilogram mass to figure out the 3 kilograms mass after the collision, which is at point C. All right, so the mass times the velocity, the mass is 1 kilogram, so the total momentum would be 20 kgms. This will equal 1 kilogram times 2 would be 2 kgms plus 3 kg times the velocity at C. Subtract 2, we get 18. Divide by 3, we get 6 meters per second would be the velocity of the 3 kilogram cart at C. Okay, so now we know that C, or the 3 kilogram cart, is going to be moving at 6 meters per second as it goes up to the hill. So now we need to figure out how fast it's moving at the top of the hill. So from C to D, we're going to have to just look at the 3 kilogram cart. And since it's moving up, I'm going to include Earth so I can look at any energies it might have. Okay, so after the collision at C to D, so C will be our starting picture, D will be our ending scenario. Okay, at C we know the 3 kilogram cart is moving at, so this is going to be kinetic energy at C of the 3 kilogram cart. This will equal the kinetic energy at D plus any gravitational potential energy at D. So we're going to have 1/2 times the 3 kilogram cart times the velocity at C squared is equal to 1/2 mass times the velocity at D plus the gravitational potential energy at D, which would be mg times y in this case. Sorry if I use h, it's a bad habit. H is still the height if I go all the way back to AB. Alright, so we know here that each term has mass in it, so we can divide all these out. Okay, and if I multiply the whole thing by 2, I'm going to get VC squared is equal to VD squared plus 2 times G times Y. Alright, we need to solve for the velocity at D. So this is going to be VC squared minus 2GY is equal to VD squared. Alright, time for a calculation. Okay, so after the collision, if it's moving at 6 meters per second, this will be 36 minus 2 times 10 times 1, which is 20, which will give me 16, and that will equal the velocity at D. You take the square root, we know the velocity at D is 4 meters per second. So we'll just have enough energy to be traveling at D. If it wasn't 4 meters per second, it wouldn't, we can answer this question. It will just have enough energy to travel at 4 meters per second at D. Just recall the purpose of this. The purpose is to really look at what happens during the collision. Now, when you have a collision, you cannot assume that energy is conserved. Therefore, we have to and must use momentum. So from B to C, when we have that collision, right, we're going to have to use momentum. Before it and after, you can use energies, but during that collision, you have to use momentum.